Related rates problems are the cornerstone of Newtonian mechanics and have been being solved since the 1600s. They are the reason that calculus was invented. Hi, my name is Tom Atwater, and in today's lesson we will be solving related rates problems. Let's look at an example. Changing voltage. The voltage V, as in volts, current I, amperes, and resistance R, measured in ohms, of an electric circuit, like the one shown here, are related by the equation V equals IR. Suppose that V is increasing at the rate of 1 volt per second, while I is decreasing at the rate of 1/3 amps per second. Let T denote time in seconds. What is the value of dV dt? Well, we were told right at the beginning, actually, that dV dt is equal to 1. The next part asks us, what is the value of di dt? And we just read up here that the value of di dt is -1/3. Okay, there's two more parts to this, so let's move ahead to those. Write an equation that relates dr dt to dv dt and di dt. Well, remember that we were originally told that V is equal to IR. And so we would want to differentiate that equation. And we would have dV dt is equal to, well, we have the product rule for the I times R. So that's going to be I times dr dt plus R times di dt. So that would be the equation that relates the derivatives with one another. The final part says find the rate at which R is changing when V equals 12 volts and I equals 2 amps. And is R increasing or decreasing? Okay, I need more space. So now, what we have is V equals IR, and we're told that the volts is 12 and the current, the current is 2, and we need to find R. R in this case is going to be equal to 6. Now, we go back to the part C answer, which is dV dt is equal to I times dr dt plus R times di dt. And what we have then, remember dV dt, we were told at the beginning is 1. And that equals I, which we were just told is 2. And we don't know dr dt. That's what we're actually trying to find. Plus R, we just calculated as 6. And then multiply times the di dt, which we were told in the problem is -1/3. So now we need to solve this equation for dr dt. Well, this is -2, which I'm going to then add to this side. And that gives me 3 equals 2 dr dt. And therefore, dr dt is equal to 3/2. So the rate, we would say, is increasing because dr dt is a positive number. Let's try another example. A sliding ladder problem. A 13-foot ladder is leaning up against a house when its base starts to slide away. By the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. A, how fast is the ladder sliding down the wall at that moment? B, at what rate is the area of the triangle formed by the ladder wall and the ground changing at that moment? And C, at what rate is the angle between the ladder and the ground changing at that moment? Let's take a look at a picture of this ladder and work out a little bit of the math that we'll use to find those answers. Here's the picture of the ladder. The wall of the house is here, and this is the ground. And you can see that we have labeled the wall as y of t. And we've labeled the movement along the ground as with x, or not the movement, but the position on the ground as x of t. My 13-foot ladder, of course, is a fixed amount. And what we would realize is that the movement along the ground is going to be the derivative dx dt. And for the wall, it's dy dt. Let me set a few more things up on this picture, though, that are going to be helpful for us when we start to solve the problem, and I won't have the picture available. So I'm going to clear those off and point out now that what we have is a right triangle in which I'm going to refer to this as x and this as y, referring to the length, because we will be using an equation, x squared plus y squared equals 13 squared, to help us solve part of this problem. The other information that I want to point out is this angle theta. We can use trigonometry to help us here, because we know that we can look at the side opposite theta, which is y. The ladder is the hypotenuse, so we know the sine of theta is equal to y over 13. So the equation that I'm actually going to end up using to solve one of these parts is y equals 13 times the sine of theta. In addition to that, I want to point out that the cosine of theta would be x over 13. And we'll be using that information as well. So all of those pieces are going to be used at some point in the solving of those three parts. Let's start, though, with part A. So in part A, what I'm going to use is the equation x squared plus y squared is equal to 13 squared, which of course is 169. What I'm going to do is differentiate this, and we'll use the technique of implicit differentiation, and we'll get 2x, and of course, then it's dx dx, and then we multiply that by dx dt. Then I have plus 2y times dy dt. And then the derivative of a constant, of course, is just 0. Now, I know some information. Remember that we have x is equal to 12. That's how far the ladder is from the wall as it's sliding down. That's the moment we're looking at. We were told dx dt, which is how fast the ladder was moving, is 5 plus 2. And then y. Well, remember we were talking about this being a right triangle? And of course, at this point, what we have is a triangle that looks like this. And this is 12, this is 13. And from your study of right triangles, you should know that that's 5. But if you don't, you can solve it up in this equation. So this would be times 5, and then dy dt. And that all equals 0. And dy dt, remember, is how fast this is moving against the wall, because y was the position on the wall. So what we'll find is dy dt is equal to negative 12 feet per second, which means that it's sliding down the wall at 12 feet per second at that particular moment, the moment when the base of the ladder is 12 feet from the wall. That was part A. Now let's turn our attention to part B, where we want to find the rate of change of the area of that triangle. Now that triangle was a right triangle, so we will use the formula that the area is equal to 1/2 the base times the height, and the height, of course, is going to be the wall, and the base is the ground. So let's do that. So the area is 1/2 base times height, which is 1/2. The base, remember, is the ground, which is x, and the height was the wall, which was y. We're going to use the method of implicit differentiation here to say that dA dt is equal to, we're going to have the product rule of 1/2, and then x times the derivative dy dt plus the 1/2, and now we take y times the derivative of x with respect to t. And now we have all of this information. So dA dt is going to be equal to 1/2. X at this point was equal to 12. Sorry, I jumped ahead of myself. So x is the distance, so that's 12. dy dt, we just calculated in part 1. That's negative 12. That's how fast the ladder is sliding down the wall, plus 1/2 of y, and we calculated y to be 5. And then dx dt is the movement along the ground, which was 5. And when we do out all that arithmetic, we end up with that the area is changing at a rate of negative 119/2 feet squared, because it's area, per second. Okay, that completes part B, and so the last thing we need to do is part C, and that's the rate of the change of the angle between the ladder and the ground. So let's take a look at that. And remember, I set that up by talking about the equation y equaled 13 sine theta. And what we're interested in here is finding d theta dt. So we know that we can take the derivative with respect to t, and the derivative of sine is cosine. Then times d theta dt. Well, remember, we talked about each of these items. That is dy dt, we calculated, and that's minus 12. That was part A. Then when I was drawing the picture of the ladder, I talked about the fact that cosine theta would be the ground length over the hypotenuse, and the ground length, it's 12 feet from the wall, so that's 12 over 13, which is the hypotenuse, the length of the ladder. And then d theta dt. So that means when I work all of this out, dividing negative 12 by 12, I find that d theta dt is equal to minus 1 radian per second. So that's the rate at which that angle, of course, is decreasing, and that's the minus sign. Okay, now let's take a look at another example. Filling a conical tank. Water runs into a conical tank at the rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? All right, I have a picture here to help us a little bit with the setup, so let's take a look at that. Here's the conical reservoir, and it said that the point was down. Remember that the water is filling up, so it's not already filled, and that's why I have H here as only part way up. We know that the whole height is 10 feet, and we know that the radius is 5 feet. But of course, with the water, which is the greenish color here, it's not at the top, so neither R is 5 nor H is 10 to begin. But we need that information, and I want to show you how. We need to know the relationship between R and H because those are two variables, and we're going to want to make a substitution. So what I want to show you right now is that if we take the ratio of R to H, that's going to equal 5 over 10. And therefore, R is going to be equal to 1/2 H. And that's a piece of information that we're going to use for a substitution in our problem. So let's get going with the problem itself, which is we're interested in the water level rising, which is we need to use the formula for volume. So let's write that down. Volume is 1/3 pi R squared H. And here's why I said we're going to substitute for R, because we know that R is 1/2 H. So this is going to become 1/3 pi H over 2 squared times H. And then that's equal to, we're going to have H squared, and we're going to have 2 squared on the bottom. So that's going to become pi over 4 times 3 is 12. And then H squared here times H there gives me H cubed. So now what I'm going to do is take the derivative of the volume with respect to time. And that means I need to bring the 3 down in front. I'm going to multiply that times pi over 12. And then it's H squared, and then dH dt. And what we're told here is that the volume was changing at 9 cubic feet per minute. It was being filled at 9, so that's our 9. Then this, of course, is pi over 4. And the height is 6 feet, so we plug that in. And then we have dH dt, which is what we're going to solve for. So when we do all the arithmetic there, we'll find that dH dt is equal to 1 over pi, which is equal to 0.32 feet per minute. And that tells us that the height of the water level rising is 32/100ths of a foot per minute. Well, now it's time for you to try a problem. I'm going to give you a problem that involves draining a conical reservoir. And so here it is. Water is flowing at the rate of 50 cubic meters per minute from a concrete conical reservoir with the vertex down. And it has a base radius of 45 meters and a height of 6 meters. How fast is the water level falling when the water is 5 meters deep? How fast is the radius of the water's surface changing at that moment? Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. Welcome back. Let's find out how you did on this. The information is similar to what I gave you, and you could have used that same picture. We know that the rate is 50 cubic meters per minute. We know that it has a radius of 45, and it has a height of 6. And those are the 3 important numbers we need to set the problem up. We also need to know the 5 meters deep when we get to the end of the problem, because that's one of the numbers that we'll plug in. So let's start off with looking at our picture and remembering that this time R over H is equal to 45 over 6. So the R is equal to 15 over 2 times H. And that's what we're going to use to make our substitution into the volume formula. All right. So we have volume, of course, was 1/3 pi R squared H, which is 1/3 pi times 15 over 2 H squared times H. And when we simplify that, we get a volume is equal to, well, we have 15 squared, which is 225. 4 squared is 4, multiplied times 3 is 12. We still have our pi, and then we have H cubed. So now take the derivative of the volume with respect to time, and we get 3 times the 225 over 12, which would make it 225 over 4, because the 3 cancels part of the 12. We still have our pi, we have H squared, and then we have dH dt. Now we make some substitutions. We know that the volume is changing at 50 cubic meters per minute, and remember that it's leaking out, draining out, so that's minus 50. Then that's going to be equal still to our 225 over 4, our pi. And this time, remember that they said that the height was 5 meters. So we plug in 5 squared, and then dH dt, which is what we want to solve for. So dH dt, in this case, once you work out all of the arithmetic, will be equal to -8 over 225 pi, and that's in meters per minute. However, the problem asked for the solution in centimeters per minute, and if you do that conversion, you will get that it's -32 over 9 pi centimeters per minute. So that completes the first part, which was to find how the rate of the height of the water was changing. The second part was to talk about how the radius was changing. So let me show you that. We have the formula for the radius, r equals 15 over 2h. And now what we want to know is how fast is the radius changing with respect to time. So all we need to do is differentiate this. So dr dt is going to equal 15 halves dh dt. And dh dt is what we just calculated in the previous section. So it's 15 halves times negative 1.13. And that gives us an answer of negative 8.49 centimeters per minute. So that gives us both the rate of change of the height of the water as well as the radius. In this lesson, we explored related rates problems using differentiation to help us solve them. Be sure to work the exercises that your teacher assigns, and we'll see you next time.